Neptune holds a record most people have never heard of: the most violent winds in the entire solar system. And the strange part is not the wind itself. The strange part is that Neptune has absolutely no business being that stormy. It sits nearly 2.8 billion miles from the Sun. It receives roughly 1/900th of the solar energy that Earth does. By every simple expectation, it should be a frozen, still, almost dormant world. Instead, it is a planet in a state of constant fury. That contradiction is what this video is actually about. Let's start with the numbers, because they are worth hearing clearly. Voyager 2, the only spacecraft ever to fly past Neptune, measured cloud-level winds ranging from about 20 meters per second, moving eastward, to 325 meters per second, moving westward. That western wind alone is over 1,170 kilometers per hour. At the edges of the Great Dark Spot, the massive storm system Voyager spotted in 1989, winds reached up to 2,100 kilometers per hour. That is roughly 1,300 miles per hour, about 1.5 times the speed of sound. No other planet in the solar system has produced a confirmed wind measurement that high. For context, the most powerful hurricanes on Earth peak somewhere around 300 kilometers per hour. Jupiter, the giant planet famous for its great red spot and its violent atmosphere, has fast winds, but they fall short of Neptune's extremes. Saturn's equatorial jet is impressive, still slower. Neptune wins this category by a significant margin, and it does so from nearly the edge of the solar system. Voyager 2 arrived on August 25, 1989, and the Great Dark Spot was the mission's most dramatic discovery. It measured roughly 13,000 kilometers by 6,600 kilometers, about the size of Earth. It looked, in some ways, like a smaller version of Jupiter's Great Red Spot, a massive rotating storm system embedded in the planet's cloud bands. Scientists were cautiously excited. They assumed it might be similarly long-lived. It was not. When the Hubble Space Telescope turned toward Neptune in November 1994, the Great Dark Spot was gone, completely. Jupiter's red spot has persisted for centuries. Neptune's equivalent lasted at most a few years. Hubble has since confirmed that new dark storms on Neptune appear to form roughly every 4 to 6 years, with lifespans of only 2 to 6 years before dissolving. Neptune's atmosphere is not just violent, it is unstable in a very particular way, churning through these enormous storm systems at a pace that has no parallel anywhere else we have observed. So the violence is documented. The puzzle is the energy source. When you look at what drives weather on the inner planets, the answer is mostly solar energy. Sunlight heats surfaces and atmospheres unevenly. That uneven heating creates pressure differences, and pressure differences drive wind. The sun is the engine. On Neptune, the sun is barely a bright star in the sky. The planet receives so little solar radiation that by the logic governing Earth or Mars, it should have almost no weather system worth mentioning. But Neptune emits roughly 2.5 times as much energy as it absorbs from the sun. That extra energy comes from inside the planet itself. Neptune's internal heat flow is about 162% of the solar power it absorbs, which means the planet is releasing a tremendous amount of its own stored heat, left over from its formation billions of years ago. That internal engine is the real source of Neptune's atmospheric violence. A mechanism proposed in science back in 1989 offered the clearest explanation for why this internal heat translates so efficiently into wind. Neptune operates in this framework as an unusually efficient heat engine. Heat is added at warmer depths and removed at the extremely cold cloud tops, where temperatures drop to around -220 degrees Celsius. The larger the temperature difference between the heat source and the heat sink, the more efficiently a heat engine can do work. Neptune's cloud tops are extraordinarily cold, and that extreme cold makes the atmospheric engine run fast. A 2013 Nature study added another piece to this picture. It found that Neptune's atmospheric circulation is confined to a weather layer no more than about 1,000 kilometers deep. That layer contains only about 0.2% of the planet's total mass. So we are not talking about planet-wide deep convection driving all of this. The action is happening in a relatively thin shell, and within that shell, the dynamics are intense. The geometry of the winds matters here too. Neptune's rotation period, determined by Voyager 2, using periodic variations in radio signals from the planet's interior, is about 16 hours. But different parts of the atmosphere rotate at very different rates. Near 60 degrees north latitude, the atmospheric rotation period is closer to 14.2 hours, corresponding to a prograde wind velocity of about 170 meters per second. At 70 degrees south latitude, a fast jet travels at 300 meters per second. The equatorial regions move more slowly and in the opposite direction. This differential rotation, where latitude bands move at completely different speeds and in different directions, is a signature of Neptune's chaotic circulation pattern. In 2016, the ALMA radio telescope array made more precise measurements using Doppler-shifted rotational emission from molecules in Neptune's stratosphere, including carbon monoxide and hydrogen cyanide. These observations allowed scientists to map stratospheric wind patterns without needing a spacecraft anywhere near the planet, confirming that the high wind regime extends well into the upper atmosphere. Neptune's atmosphere is primarily hydrogen, making up somewhere between 77 and 83% of it, with helium accounting for most of the rest. Methane is present at only about 1 to 2%, but that small fraction is responsible for the planet's vivid blue color. Methane absorbs red light and reflects blue back into space. It is a remarkably small ingredient to define an entire planet's visual identity. What makes Neptune genuinely strange, when you step back and hold all of this together, is what it reveals about our assumptions. We instinctively connect a planet's weather intensity to its proximity to the sun. More energy in equals more dynamic atmosphere. Neptune breaks that intuition completely. Its distance is not a weakness. The extreme cold of its cloud tops is actually the other end of the thermodynamic gradient that makes its heat engine so effective. The sun's near absence is, in a paradoxical way, part of what allows Neptune's internal heat to drive such extreme atmospheric dynamics. We have only visited Neptune once. Voyager 2 spent a matter of hours in close proximity to a world it took 12 years to reach. Everything we have measured since then has come from Earth-based telescopes and observations like ALMA, watching a planet 4.5 light hours away. The storms that formed and dissolved in the decades since 1989, the jet streams at speeds no other planet matches, the transient dark spots cycling through their brief violent lives. Most of this has been inferred from signals collected across an enormous distance. There are proposed missions to return to the ice giants. If one eventually reaches Neptune, it will arrive at a world whose basic behavior we understand in outline, but whose details remain, by any honest measure, mostly unknown. For now, Neptune remains the solar system's most powerful storm engine, running on ancient internal heat at the edge of the sun's reach, almost entirely unwatched. The question worth sitting with is this: if a planet this far from its star can sustain wind speeds that exceed the speed of sound, what assumptions about energy, distance, and weather are we still carrying that the outer solar system has not yet had the chance to break? If you enjoyed this video, consider subscribing to the channel.